So, first of all, let's begin by talking about the difference between a sequence and a series. So, the difference between a sequence and a series is that the series is the sum of a sequence. So, for example, if I have a sequence of numbers 1, 3, 5, 7, 9, then the series would be 1 plus 3 plus 5 plus 7 plus 9. Similarly, if I had a sequence 3, 6, 12, 24, then the series would be 3 plus 6 plus 12 plus 24. So a sequence is basically just a list, and a series is the sum of that list. Now, in particular, we call our first sequence that I wrote here the arithmetic sequence, or a arithmetic sequence, and we call the second one a geometric sequence. So if we take a look at the first sequence, we can see that the difference between each number is always 2. And that's an arithmetic sequence. So an arithmetic sequence has a common difference. In our case, this arithmetic sequence had a common difference of 2. Now, our second sequence here, that's called a geometric sequence. So we can see that for each number, the next number is the previous one times 2. And in this case, the geometric sequence has a common ratio. So the ratio between two consecutive terms is always the same. We usually call the first term in an arithmetic sequence U1. And the second term will be U2, U3, U4, and so on and so forth. Now, the arithmetic sequence has to have a common difference, and we denote that common difference using the letter D. So the common difference is D, which means we can represent U2 equals U1 plus D, and U3 would be U1 plus 2D, so on and so forth. In general, UN would be U1 plus N minus 1 D. And you might think, wow, this N minus 1 is kind of annoying. So in some mathematics, when they represent arithmetic sequences, they would instead start with U0. So they would call the first term actually U0. So then UN would just be U0 plus ND. But on the IB formula booklet, this is the equation that you're getting. So this will also be the one that I will be using. So now let's talk about finding the sum of an arithmetic sequence, or the arithmetic series. So let's say we have an arithmetic sequence 1, 3, 5, 7, 9, 11, 13. How can we find the sum of this series? Well, one way we can do is we can add them all together. Another way that we can do, which simplifies a lot of our calculation, is if we were to write the elements backwards, like this, we can see that the numbers in each that are lined up, or in each column, they add up to 14 all the way through. So that means if this was if the sum was equal to this, then this would once again also be the sum. So that means that 2 times the sum is equal to 14 times the number of elements, which since there are 7 of them, 14 times 7. And that means S is equal to 49. Knowing that, let's try to derive a general form for the sum of an arithmetic sequence. Let's say we have a sequence where it's u1 plus u1 plus d plus u1 plus 2d all the way to u1 plus n minus 1d. In other words, this is the term un. So what we can do is we can write everything backwards. un minus 1, un minus 2, all the way to u1. And when we sum each of these up, we should get 2u1 plus n minus 1d times the number of elements that are here, that's n, equals to 2 times the sum. And that means the sum is equal to n over 2 2u1 plus n minus 1d. Or if you want to represent this using u1 and un, this could be n over 2 times u1 plus un. So you can also use this to find a general term for if you want to find a general term for the sum of the elements that are in between an arithmetic series. So instead of starting with the first element, you want to make it so that you start with the third one, and then maybe you can end with the 7th one. And in the end, you can still use this formula here. You just have to take note of how many elements you actually have. So now moving on to the geometric sequence. The geometric sequence we usually represent, once again, with u1, then u2, u3, so on and so forth. But this time, instead of having a common difference, it will have a common ratio, and we call that r. So we can represent u2 using u1 times r. u3 would be u1 times r squared, and therefore un would be u1 times r to the n minus 1. Once again, some math textbooks might start with the term u0, therefore this would also be u0 times r to the n. But I will stick with starting with the index of 1. Okay, so now let's try to find the sum of a geometric sequence or the geometric series. So once again, let's start with our first term, u1 plus u2 plus u3 all the way to un. And let's let this equal our sum. So we're going to do a little bit of algebra here to derive the sum. So first of all, we're going to want to write it in using the common ratio. So we're going to write u2 as u1r, u3 as u1r squared, all the way to u1r squared, all the way to u1r to the n minus 1. Then we're going to multiply this equation here on both sides by r. So we get r times s equals u1r plus u1r squared plus u1r cubed all the way to u1r to the n. So if we take a look at our two equations here, number 1 and number 2, we can see that they're pretty similar in that a lot of these terms are the same. So that prompts us to try and subtract the two. So let's do the second equation minus the first one. That gives rs minus s equals, and you'll see that all of these terms will cancel out when you subtract them. And you're just left with u1 times r to the n minus u1. And you can simplify this to u1 times r to the n minus 1. And therefore, r minus 1 times s equals u1 times r to the n minus 1. And therefore, s is just equal to u1 times r to the n minus 1 over r minus 1. Now, note that right here, we'll see that r minus 1 is in the denominator. In fact, that means that r cannot be 1, because that will make the denominator equal 0. And this makes sense. If r equals to 1, then our geometric series would just be the exact same thing. We would have u1 for all of our terms, and that doesn't really make sense. Now, as an extension from the normal geometric series, let's look at the infinite geometric series. So this is when you have u1, u1r, u1r squared, except it doesn't stop at u1 r to the n, and it goes on forever. So obviously, in this case, we have a condition. That is, r has to be smaller than 1. And in fact, r can be negative, so the absolute value of r is smaller than 1. This ensures that as we move on with our terms, our numbers are going to be decreasing. Because if r is smaller than 1, as we take r to a larger and larger power, that number becomes closer and closer to 0. So the terms are gradually getting smaller and closer to 0. If r was equal to 1 or greater than 1, then our geometric series would not be summable. Instead, it would go off into infinity. So, once again, if we let this equal our sum, we can write the sum to be u1 times r to the n minus 1 over r minus 1. Or we can also write this as u1 times 1 minus r to the n over 1 minus r. Now remember, this is for a finite geometric series, where we're just summing the first n terms. But now let's extend this a bit. Let's think if n was going to infinity. Now this is a calculus concept as a limit, but for the sake of this video, let's just think that n is getting really, really big. Now, as n gets really, really big, u1 is not going to be affected. Neither is 1 minus r. But it will affect r to the power of n. And since we've set r to be a value smaller than 1, when you raise r to a really, really big power, that number will almost be 0. So, therefore, s would just be u1 times 1 over 1 minus r, because r to the power of n is practically 0 at that point. So once again, this is the formula for the infinite geometric series. So, as a recap, let's summarize all the formulas that we've just came up with. Now, all of these formulas will be on your formula sheet, so you don't need to memorize these. However, knowing how these formulas are derived will help a lot in your problem solving, and it will help you find motivation when you're stuck on a hard problem. And that's it for this video. Thanks for watching. Goodbye.